Okay, so I'm just going to run through the investigations from the beginning of Unit 4 here, investigating sinusoidals. You can see I've got my handy dandy Desmos up, and I'm just going to set the graph settings here to be a little bit more appropriate. There was a video on how to do that in case you missed it, but the keys are when I look at the equations that I'm going to be dealing with, right now I've got up to 4 down to -4. That seems pretty good. But my x values, I would like to have them appear in terms of radians. So I'm going to start my radians at -2 pi. And to do that, I just type in -2 and the word pi, pi. Over here, I'm going to go 2 pi as well. And then I'm going to have the step be pi. And so you can see now that I can see an x-axis that's a little bit more appropriate for what we're doing. What I'm interested in seeing is sort of what I can pull from doing the investigation. Of course, you want to recognize that an investigation is not an assignment. You're not just trying to get through and make sure you have the right answers. You want to take a look at what's going on and determine from that what you can learn so that you can then go further with it. So sine, this is the basic shape of sine. It's a wave. It starts at 0, goes up to 1 at pi over 2, down back through 0 at pi. Those are the values we probably know from quite a while ago. Going the other way, of course, the same thing. And if we did extend this out, let's zoom out, you can see that the pattern just obviously continues forever. See if I can get back to approximately where I was. That's not too bad. Maybe a little bit closer. And I've got 2 pi to -2 pi again. Looking at some other options, cos. Cos looks like the exact same curve, except it's shifted over. And again, that makes perfect sense because we know that things like sine of, say, pi over 3 is the same as cos of pi over 6. So sine of 30 is the same as cos of 60. Sine of 90 is the same as cos of 0, and so on. So here's my sine of 90 in red. My cos of 90 is 0. Again, it's what we would have had at the 0 here. And then if we look at tan, just for the sake of having seen it, essentially there are asymptotes at pi over 2, 3 pi over 2, -pi over 2, and so on. The graph basically approaches each of the asymptotes from the left or the right, and goes up as it approaches from the right, or sorry, as it approaches from the left as it's going right, and comes down to the edge as it goes left. Just recognizing that's important for now. One of the questions I received was, how do I write the domain for this? The range of tan, of course, is all values of the real number system. This number, the y values continue here down to, well, forever, and continue up here forever. The x values are a little bit trickier because -pi over 2 is not okay, pi over 2 is not allowed, 3 pi over 2 is not allowed, and so on. And as we've seen, that continues out. So if we look at it here, again, exact same pattern. And essentially what we would tend to write is this. The domain is equal to x belongs to the real, so x can be any real number, such that x does not equal pi over 2, and any combination of pi's added on to that. So pi over 2 plus pi would get me to 3 pi over 2. Pi over 2 minus pi, minus 1 pi, would get me to -pi over 2. Minus 1 more pi would get me to -3 pi over 2, and so on and so forth. So this would kind of be your fairly official way to write this. X belongs to the real number system. X cannot be pi over 2 plus any combination of n times pi, where n can be any integer. At 0 you get the pi over 2, at 1 you get the 3 pi over 2, at 2 you get the 5 pi over 2, and so on and so forth. Get rid of that. So those are sort of the first 3 parts. What is sine, what is cos, what is tan? And we'll move forward into the second investigation then, which is really the more important one at this point. Here's sine, and the first thing it asks us to graph was sine plus 2 and sine minus 3, so these two. So essentially what we're looking at again is, what does this tell me in terms of how the plus 2 affects the graph? Clearly the only change from the first graph, the red graph, to the green graph is that the number 2 has been added on to the end. And so essentially, if we look at, I've got 0, 0 here, up here I've got 0, 2, here I've got pi over 2, 1, here I've got pi over 2, 3. Fairly obvious, I guess, that the y value, whatever the y value was from the original graph, has been increased by 2. And of course, looking at the equation itself, that makes perfect sense. Take exactly what we had before for y. Y was equal to sine over x, remember? Take exactly what we had for y there and increase it by 2. The whole graph moves up 2 spots. Okay, so I just sort of changed the grid a bit here so that you can see this a little bit clearer. There's the 2, this one up to 3, and 1, and so on. Should be no surprise then, when I subtract 3 instead, the values that I had in my original, 0, 0, down to 0, negative 3, pi 1, down to pi negative 2, and so on. The second part of the investigation said to do 3 sine x, negative sine x, and 0.5. So these 3 here. I guess we should do them one at a time. Given that the original is the red here, what's happened? Well, again, should be fairly obvious. This is saying take whatever I had before for sine x, or sorry, sine x was what I had before, and multiply it by 3. And so that becomes my new y value. 0 times 3 is 0. Over here at pi over 2, I had the value 1 for y. Multiplied by 3, I get 3. And at every point in the graph, essentially this is just saying take the existing y value, triple it, multiply it by 3, and so the graph goes up 3 times as high, down 3 times as low, and so on. Negative sine x. And again, just sort of thinking these through logically, we should be able to figure out what's going to happen. Wherever I had a positive 1 before, I now have a negative 1. 0 times the negative 1 is still going to be 0. Where I had a negative 1 before, multiplying that by the negative 1 out front, I now have a positive 1, and so on. The entire graph is flipped, if you'd like, across the x-axis. But again, the logic behind it is pretty straightforward. This is negative times the existing values. In other words, anything that was negative becomes positive, anything positive becomes negative. 0.5 then, and again, won't go through this one, but same idea. This is a half times the existing values, so where I was at 1, I'm down to 1/2. Where I was down to negative 1, I'm only down to negative 1/2. And so on. Minus pi over 2. So this one's a little different, perhaps. If we can sort of think of it in terms of how does the pi over 2 specifically affect the graph? So if I look at a value like this one, I'm at negative 3 pi over 2. I want to, essentially it's saying subtract pi over 2, which suggests perhaps to most people that the graph would move to the left. But of course you can see that it hasn't happened that way. We've actually moved to the right. And again, this is pretty similar to what you've seen before, probably in grade 10 when you're dealing with transformations of parabolas, quadratics. The negative value, the subtraction in this case is sort of what is required to do to get back to where we were. So if we think of maybe an easier spot, this pi over 2, when I subtract pi over 2 minus pi over 2, I end up back at the 0. So essentially what's happening is my graph is shifting to the right, the pi over 2. This one actually was supposed to be a plus sign, although I wrote negative in the notes. And of course you can see the same sort of thing. When I have a plus pi over 4, my graph is actually shifted to the left. When I had the original minus pi over 4, the graph shifts to the right. And again, the idea is that I have to start somewhere else, subtract the pi over 4 to get the value that I'm looking for, essentially, or to get the sign value that I'm going to use. And so if I start at pi over 4, subtract pi over 4, I'm back to the 0. If I start at whatever this ends up being now, 3/4, oh yeah, I guess I knew that, 3 pi over 4, I subtract the pi over 4, and I'm back at the 2 pi over 4, or pi over 2, where that will be used in the calculation of sine. Okay, so last one. And this one's kind of an interesting one. I see the number 4 being included now. It's multiplied by my x, obviously, but the only change between the original sine x and the purple equation is the fact that there's a 4 involved. And so essentially what we have to determine is what is happening now. Well, it looks like, if we sort of think about the original graph going all the way out here, I'm xylophoning it. I'm squishing it to the point where now a complete cycle is just in a distance of pi over 2. And so going from the fact that I originally had a full cycle going starting at 0 all the way up to the top, all the way down to the bottom, and back to 0 over a distance of 2 pi, I now have 1, 2, 3, 4 full cycles in that same distance. And that's essentially what this number is telling me. How many full cycles will be in the distance 2 pi that is the standard distance for a cycle of a sine curve. I'm going to jump ahead here and use the 0.5, and sort of, if we think it through the exact same way, in the standard 2 pi distance, where we would normally have one full cycle, you can see now that we have exactly half of a cycle. If I zoom out, I had one full cycle here, 2 full cycles in 4 pi. I now have one full cycle in 4 pi, or again, only half of a cycle, 0.5 of a cycle, in the 2 pi distance that I started with. Okay, so last one here, this negative x, what's going to happen here? Well, again, if we think it through logically, I think about what my original x value was. So here, if I have an x value of pi over 2, the equation says I'm going to make that negative, so essentially it goes to negative pi over 2, and then I'm going to take the sign of it, which means I'll have the value negative 1. So instead of having a y value of 1 here, I'm going to have a y value of negative 1 right there, and so that means that the negative x will mirror my image through the y-axis. So hopefully that helps a bit. Again, what you're looking to do is sort of use the fact that we know what this now does, adding a value onto the end raises and lowers my graph, multiplying by a number out front, stretches and compresses through the y direction. Obviously here we're shifting left and right, or right here, and here we're looking to compress in the horizontal. Specifically, this number is the number of cycles in 2 pi, and we'll use that to determine things like the period. The period, as you've seen before, is the actual distance that one cycle covers. So when we talk about this graph, for example, 4 is the number of full cycles in 2 pi. The period of one cycle, the amount of time it takes to complete one cycle, the amount of distance, I guess, it takes to complete one cycle is pi over 2, which is 2 pi divided by 4.